Good afternoon, everyone. My name is Kedar Rao. This is my second video lab, and it is motion with gravity and drag. The main objective for this lab is to measure the motion of two objects, one that falls fast and one that falls slowly, and look at the effects that just force of gravity has on them, and both the force of gravity and the drag force have on the objects. Um, the observations for this lab was that terminal velocity is only achieved on the slow falling object because there is more drag. The fast-dropping object does not experience much drag, hence there is no terminal velocity. So as you can see here, we have my two objects, one that is falling fast and one falling slow. The one that's falling fast is on the left, and the one that's falling slowly is on the right. The fast-moving object is actually a tube of chapstick, and has a diameter of 0.065 meters. So we can watch this. And we can watch the paper fall. It's actually folded in half, so it has a diameter of 0.108 meters. So you can see that I have set the origin of the axis at the beginning of the descent. So it starts at vector 0, 0, 0. And the objects are obviously moving in the negative y direction. So it'll have a negative velocity. So here are the codes for the two objects. On the left is the chapstick, and on the right is the code for the paper. So let's watch what happens with the chapstick. So as you can see here, the graph is curved. Now let's watch what happens with the paper. So those two graphs you just saw were basically a representation of the objects falling with just the force of gravity. So all it takes into account is the mass of the objects, and the mass of the chapstick was 0.004 kilograms, and the mass of the paper was 0.00025 kilograms. These objects are very light, and I used a delta t of 0.01 for both of them because I felt like 0.01 increments for each would be a good representation. And for the chapstick, it took about 0.6 seconds to fall. However, the paper, being much lighter and having more drag, took about 1.4 seconds to fall. So I have while t is less than 1.4 for paper, and while t is less than 0.6 for the chapstick. So now we're going to look at the ball falling with both gravity and drag. So drag is basically in the opposite direction of gravity, and it can be found by multiplying the opposite of the magnitude of the ball's velocity, so negative magnitude of ball's velocity, times the unit vector of the ball's velocity, which is just 0, 1, 0, times the constant of proportionality b. And you do this for both the chapstick and for the paper. So now let's take a look at the graph for the chapstick that includes both drag force and the force of gravity. So as you can see, the graph is pretty sloped, which means that the drag force isn't close to the force of gravity, which means that there is an acceleration showing, as you can see by the nonlinear curve. And we'll look at the graph for the paper with the same instances. As you can see, the graph is linear, which means that the drag force and the force of gravity is very much equal. In this case, the velocity is linear. So now let's take a look at how our computational models lined up against our observed in Tracker. So the blue dots are the Tracker model, and the red dots is the predicted with gravity and the predicted with drag. So the top one is just with gravity. As you can see, the prediction did not exactly line up with what we observed. This is because drag is not taken into account. As you can see below, the observed and the predicted with drag and gravity is pretty much the same. So now let's take a look at the paper drop. So as you can see here, the one on the top, the one with just the observed and the predicted with gravity, the observed is much more linear than the one with just the gravity. However, on the bottom, when it includes drag, you can see that the observed is pretty much lined up with the predicted with drag and gravity. Now you can see that drag actually has a huge impact on slower moving objects. So what does this all mean? Why are we doing this? Well, you start with the fundamental principle F net equals ma. And the net force in this model is the force of drag plus the force of gravity. When the magnitude of these two are equal, you find a terminal velocity, as you can see in this instance for the paper, where the slope is very linear. However, when the force of drag and the force of gravity are not equal, you'll find a... So now for the what if question. What if the slow dropping object, the paper, was thrown down with an initial force? So if that were to happen, then the drag for the object would actually increase so that it would start off at a non-terminal velocity, but then soon quickly become a terminal velocity. So in conclusion, basically an object that has very little drag will not experience a terminal velocity, such as the chapstick. However, an object that does have a lot of drag, whose magnitude is equal to the force of gravity, will experience a terminal velocity as the paper did.